first thing we're going to go over is how to do titrations. So in chemistry, when you are adding an acid to a base or adding a base to an acid solution, that is what a titration is called. So there's 3 different types of titrations, and they each have different ways to go about doing them. The first one is a strong titration. The second one is a strong, weak titration, and the third one is a weak titration. And all 3 of these can be done with like a strong acid and a weak base, or a weak acid and a strong base. It just depends, but the process is ultimately the same for all of them. In this video, we're going to focus on the strong and weak titration. And the key component about this is that it forms a buffer. And a buffer solution is just a solution with a weak acid or a weak base and the salt of the weak acid or the weak base. So it's basically just a compound and its conjugate. So an example would be, I'll just write it out. An example of this would be CH3COOH. And then its conjugate would be CH3CONA. So it's basically just replacing this H right here with a different salt, which is why it's the conjugate.
Okay, examples of strong acids include hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric acid, nitric acid, perchloric acid, and sulfuric acid.
And then examples of strong bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and francium hydroxide. And then you'll notice that for the strong acids and strong bases, they will all belong to a certain group on the periodic table. So
Okay, so strong acids mostly pertain to halogens, except no fluorine, and they have a pH of 2 or below.
And then strong bases mainly include the alkali metals, and then additionally to that, transitional alkali earth metals are also considered strong bases, but they do not dissociate 100% in water. And additional to that, strong acids and strong bases basically just mean that these acids and bases are able to easily split and completely 100% dissociate in water. So that's just basically what a strong acid and strong base indicates. Okay, so the first titration example that we are going to do is the titration of a weak acid with a strong base. So this is kind of the wording of what a problem would sound like. You're titrating a 15 milliliter solution of 0.110 molarity nitrous acid, which is HNO2, and the Ka is 4.5 times 10 to the negative 4th, and they will almost always give you the Ka or Kb value. With a 0.250 molarity KOH solution, find the pH of, and then you're specifying the pH at these various points in the titration. So here in purple, I have the first step, which is to find the equivalence point, and the equivalence point is just when the moles of KOH equals the moles of nitrous acid. And to find this, you just do the basic titration formula, which is liters times moles equals moles times liters. So first you do that of the nitrous acid, which is 50 milliliters and 0.110 molarity. And you set that equal to 0.25 molarity, which you get in the problem, and then you solve for x, which is the amount of milliliters needed to make this problem true. So when you do the math, you find that the answer is 22 milliliters, and that means that this right here is the equivalence point. And another important point along with this is the halfway point, which would be 11 milliliters. So these are the 2 most important points in your titration in that step. Okay, so the second step that we're going to do is we're going to do the titration of 0 milliliters of KOH. And before we do that, I just want to go over like these different things I have written in red. So when there's 0 milliliters of KOH, that means that absolutely no base has been added. So the solution is just a weak acid, which we know from what they give in the problem. Then when 6 milliliters of KOH are added, that makes it a buffer solution because, like we said earlier, it's just a conjugate of the solution or the compound. And then we have halfway point, and then it's a buffer again in between the halfway and the equivalence. Then the equivalence point, and then by the end, after the equivalence point is reached, that's when it becomes a strong base, which is what you're putting into the solution. So this is part A, and I just wrote out the reaction that's happening, which is the dissociation of nitrous acid into hydrogen and NO-2. And on the left, we have the Rice table. So you start with the initial concentrations, which is 0.10 molarity and 0 for the two products. Then you subtract X, add X, and you know how to do a Rice table. So then we're going to set up the Ka equation, which is the Ka is equal to the product squared over the reactant. So that's X squared over 0.10. And then when you solve for X, you get 0.00703. And that is equal to H plus concentration. And when you take the negative log of that, you find the pH at the first step, which is 2.15. Okay, so now we're on to part B, which is where you add 6 milliliters of KOH, and that forms a buffer. So buffer solutions are a little bit more tricky. They have a couple steps, and the first one is writing the equation. You don't really have to get the equation completely right. Honestly, it's just more about the process. But you're adding nitrous acid with potassium hydroxide, which forms water, and this compound right here. So first we're doing the titration of these two. So you have 50 milliliters times 0.100 molarity, then 0.250 molarity times, I don't know what that says, 6 milliliters, my bad. And so then you have a number of millimoles, and it's all right to do it in millimoles since it's just comparative and you're going to convert it back by the end. So this is how many millimoles of HNO2 you have, and this is how many millimoles of KOH that you have. So first thing you're going to do is you're going to take the 5.5 and subtract 1.5 from it, because that's how many millimoles you are losing from the HNO2, which means that 4 moles remain of this HNO2 acid, my bad. So then that means 1.5 millimoles are going to be added to this KNO2. So, like I said, 1.5 millimoles. Then you're going to find the molarity of both of these. So you just divide it by 56 milliliters, which is the 50 plus the 6. Don't forget to add those two numbers together because you are increasing the amount of milliliters with each step. So then you find the molarities of those two compounds. So in the end, you should have 0.07143 molarity of HNO2 and 0.0268 molarity of KNO2. Then we're going to use this equation down here, which is basically just the nitrous acid in equilibrium with regular acid and nitrite. So you plug in the two molarity values into the Rice table because you already have an existing amount of the NOH from the earlier part of this, so you can't have it at 0 already, which is why you start with the 0.07143 and the 0.0268. So then your Ka equation will look like this, where you have the 0.0268 times X over 0.07143 equals 4.5 times 10 to the negative 4th. And I didn't write out all the math, but when you do that and you find the X and you use the negative log of the X, you get a pH of 2.92. Okay, so now we're going to move on to part C, which is the halfway point, as I said earlier. And for the halfway point, it's just very simple. It's the easiest step, and all you have to know is that the negative log of the Ka value is equal to the pH of the solution at the time. So the negative log of 4.5 times 10 to the negative 4th is equal to 3.34, and that is your pH. Now we're just going to go straight to part D, and I'm not going to do part D. Okay. Now we're going on to part D, but actually I'm not going to do part D with you guys because we just did a buffer problem, and I'm going to let you guys try it on your own and see if you can do it. So I'll just tell you what the correct answer is. You should get 3.763 for the pH, so I'll just write it here. Part D is 3.763 equals the pH. Okay, so now we're on to part E, which is the equivalence point. The equivalence point is pretty similar to how you do a buffer, but a little bit different. So you have the same equation that we've been using for the first part, and we're just going to do the regular titration, 50 milliliters times 0.110 molarity is equal to 5.5 millimoles, and 22 milliliters times 0.250 molarity is equal to 5.5 millimoles. You should get the same number for this because they are at the same equivalence point. So then the millimoles of KOH formed are going to be subtracted from the HNO2, and they're going to be added to the product side, product side. And that means that you have 0 millimoles of product and 5.5 millimoles of product. My bad, it's 0 millimoles of reactant. So after that, you're just going to do the same thing we did earlier, and you're going to divide by the milliliters, which is 72. Don't forget to add that 22 to the 50. So then you get a molarity of 0.0764, and you're going to transfer that back over here to the second equation, which is NOH2, turning into HNO2 plus OH minus. It's important to recognize that now, at the equivalence point, the weak acid has turned into a base, which is why OH is forming. So just keep that in mind. So you do the Rice table where you subtract x, add x, and you do your equation. But once again, the x squared over 0.0764 is equal to the Kb instead of the Ka. And you guys know how to find the Kb when you are given only the Ka, which is 1 times 10 to the negative 14th divided by the Ka value. And that gives you a Kb of 2.22 times 10 to the negative 11th. So I just did the basic things we did earlier, and I didn't write the math for it again. So you just take the negative log of that x value, and the pH is 8.115. So don't be worried if it's a really big jump from this buffer right here to the equivalence point. It's supposed to be a big jump because it's turning from it's turning from an acid into a base.
Okay, so for the last step, we're going to be using the same equation we've been doing the whole time. So what we do is that we multiply our 50 by our 0.11, and you get 5.5 millimoles, and then you do your 26, since that's the last one of the KOH this time, and you multiply that by the 0.25, and you get 6.5 millimoles. So what you do is that since 6.5 is the bigger one, you subtract 5.5 from that, and you get 1 millimole, and then from there, you divide it by 76 milliliters because it's your original along with your added, and then you get 0.0132 molar. And so in order to find the pH from this, you do the negative log of this number, and you get 1.879, but since this is the POH, in order to find the pH, you do 14 minus this number to get 12.121 for your pH.
Thanks for watching!